Hi, welcome to chemistry. Normally this will be filmed before a live class audience, but we had some audio issues last week, and therefore I'm just filming this between you and I. So it will be different when you see the other lessons, but this one, it's just going to be you and I, so I just want you to know that. And that's why I'm actually going to end up having the same clothes on for this week as I will for next week, because I'm actually filming this the same week because of the difficulties that we had. Hopefully you guys have all watched the creation interpretation foundational videos that I asked you to watch, and you've also watched the introduction to chemistry, where you've been told to have a calculator that you can use easily so that you can get in between all of the different, shame on me. Let's start in prayer. Father God, we thank you so much for today, Lord, and I thank you for the privilege of being able to share chemistry with these young people. Lord, I'd ask that you would bless them wherever they are, bless their families. Help them to grow in their relationship with you, Lord, and hide your word in their hearts and minds so that they might not sin against you. Please, Lord, bless them with loving you with all their heart and soul and mind and strength, and loving their neighbors as themselves. And Father, as we do chemistry now, I pray that I would be clear and that you would help them to understand, and that above all, Lord, that all these things would work together to bring you glory in their lives and to bring them closer to you. Thank you so much, Lord, for the privilege of living where we do and for the privilege of homeschooling. And I just pray that you will bless these young people and their families. In Jesus' name we pray, amen. Sorry about that. We always start in prayer. Okay, now, make sure that you've looked at your syllabus. Make sure that you know that you try to memorize these in as easy words than your own words as much as possible. Have a calculator that you are very familiar with and can use to do exponents. You'll have to be able to manipulate exponents, positive and negative. And make sure that you have all those things in place. And let's go ahead and read. We're in the third edition. That's why we had to... third edition. And so we have to make a new video because we're on the third edition. And that's great. So on page 1, let's look at that together. And it's measurements, units, and the scientific method. Now here he's defined for us matter. And I say he. I don't know if the author's a he or a she, but I'm used to J. Weil, so forgive me if I do that. But we're told that matter is anything that has mass and takes up space. Now, that's a very good definition, and it's a short definition, so I think we're going to go with that definition. And so on the next 2 pages, we have 2 experiments that I will not do in class because they're just, one of them's too hard. Experiment 1.1, he wants you to manage to balance a ruler, and then you're going to tie 2 balloons on it and make sure it's balanced, and then you're going to blow one of them up and put it back on. And what's going to happen? The one with the balloon is going to be heavier. And so if you have it balanced, and then you blow up one balloon and leave a not blown up balloon on one end, it's going to tip in the direction of the blown up balloon. And what that shows us is that air has mass. And in your syllabus, you have been told how to do a lab write-up. Mine is different than what's described in the book, and so I'd rather you follow the procedure that I gave you, which was your purpose, what you're trying to learn. And in this lab, the purpose is stated right there. We're going to determine if air has mass. The procedure would be a very brief description of what you're trying to do to actually do the lab. Your observations and calculations. Here, your observation would be that the one with the air in it was heavier because it bent down in that direction. And then your conclusion would be air has mass, and so possibly it's matter. Then we go to experiment 1.2. In experiment 1.2, you were supposed to take a glass, put a paper towel in it, put it down in a sink of water, and you saw that the paper towel stayed dry. And then if you were to take your glass and turn it sideways slightly, the water would get up in there and it would make it wet. And so this actually tells us that air takes up space. So the 2 parameters of matter is that it has mass and takes up space, and air has mass and takes up space, and therefore air is matter. Now, what is all around us that is not matter? And your book tells you it's light. And light is all around us. It takes up space, but it doesn't have any mass. And so light is actually energy. It doesn't have mass. And so it is not matter. It's energy, once again. So next we have units of measurement, because we can measure the matter. And that's one of the ways that we can study the matter is by measuring it. Now, we're going to use the metric system, but we're going to compare it to the English system. And he tells us here on page 5 that if you have an answer that doesn't have the units attached to it, even if you have the right number, your answer is wrong. And that's absolutely true. If you do not have the correct number and units, your answer will be wrong. So it's very important that you make sure that you put your units with everything that you do. On page 5 and 6, he introduces the idea of the different units that we will be measuring, not only the different units, but the different aspects of matter that we'll be measuring. And we see that the first thing is the mass. And the mass is how much actually is in something, how much makes it up. And so, let's see, I'm going to bring this back here. So the mass, when we study it measure it in the English system, mass would be slugs. When we do it in the metric system, mass would be grams. And a gram, he tells us that a gram weighs approximately a housefly, which is kind of gross. Nobody wants to hold a housefly. So if you think of a dollar bill weighs a gram. So that gives you a good idea. Okay, and then if we were measuring distance, then distance, if we did it in the English system, would be feet. We're all used to that. A ruler is about that long. It's a foot. If we did it in the metric system, we are going to actually measure it in meters. And so here I have a meter stick. And that is the length of a meter. That long. Now to give you an idea, on this side, it is marked off in feet. And you see that the yard ends right here, where there's no numbers right here. And so a meter is just slightly larger than a yard, isn't it? And so that gives you an idea of the size of the meter. And so then we look at volume, and volume is our next way to measure matter. In the English system, we use a gallon. In the metric system, we use a liter. And so for the English, it would be a gallon, and for the metric, it would be a liter. And so that's how we would measure those. And then, thank God for time, it's in seconds in both instances. So we don't have to learn two different methods there. It's just going to be in seconds in both places. You are expected to know this. You're expected to know what the different units are that are used for this. In this, it did describe the difference between mass and weight. And mass is how much matter makes something up. Weight is how the gravitational force pulls on that matter. And so if I were to weigh myself right here, I would weigh a certain amount. And then if Scotty transported me to the moon and I stood on my scale, I would seem to weigh much less, even though my mass hadn't changed because I wouldn't have exercised and eaten properly, etc. I would weigh a lot less because the gravitational pull of the moon is so much smaller than the Earth because it's a smaller object. Therefore, weight is actually a force. When you get to physics, weight's a force because it's the mass times the gravitational pull, whereas mass is strictly the amount of matter that makes something up. That confused me a little when I was going through college, so I thought this was a very clear presentation. Part of the reason I was confused is because when we use the mass scales, we're actually weighing something. But you have to remember those mass scales were calibrated for the gravitational pull of the Earth, and therefore they're actually already taking that into account, and they're actually measuring mass. I just wanted you to know that. So when we do experiments, that will come into play. Then when we manipulate units, turn over to page 8. We use what's called a prefix system in the metric system. And it's a lot easier because metric is on base 10. And so that prefix system allows us to add prefixes to the basic units, and then we can go up and down with those units. So let's look. On table 1.2, it tells us, look at the bolded ones. Those are the ones you're going to have memorized. Milli means 1/1000th. That's what milli means, is 1/1000th. And so that's actually 1/1000th, isn't it? And there's 1,000 years in a millennium. There is, with centi, there's how many years are there in a century? 100. So centi is 1/100th, or it can be written this way. Okay? Kilo, you also have to memorize. Kilo means 1,000, so it's a larger number. So let me show you what this might look like. When we look at volume, we said this was our base unit, is a liter. This is a little 1 centimeter cube, and so if I were to fill it up and I were to pour it in here, it would take 1,000 of these to fill this. Therefore, this is a milliliter, and this is the liter. If I wanted to see a kiloliter, I would have to take this and fill basically a hot tub up, and that would be a kiloliter. And I actually have a little centiliter here. If I took this and I filled it 100 times, I would fill this up. This is a centiliter. All right, so I showed you those differences with a liter. With the metric on the, with the meters, once again, this is your metric ruler. But if you'll look closely, you'll see that it is marked off 1 to 100. See down there it says 100? So this is already marked off to centimeters. And then once again, I'm going to show you a close-up again. If you look here, each centimeter is marked off by 10. It's marked off to millimeters. And so this meter stick is actually marked to millimeters. And then centimeters are numbered, and then this is a meter. And then if I wanted to do a kilometer, I'd have to walk off 1,000 of these, which is around half a mile. It's pretty good distance. And so the kilo makes it bigger. And you can add these prefixes to any one of the base units we talked about. If you were measuring something bigger than a housefly or a dollar bill, then you'd want to use kilograms, because that would be closer to what we would think of as a pound. It's a closer unit. And then there are other, on table 1.2, there are other prefixes here, but you don't have to memorize them. They'll give them to you. Now, I had a student ask last week in class, and I thought it was a very good question. She asked why, if there's 1,000 years in a millennium, then why is it 1/1,000th, or 100 years in a century? Why is it 1/100th? Well, all I can tell you, because I don't know all about this, but I know that the prefixes that are Latin are fractional, so they're the smaller numbers, and the prefixes that are Greek are the bigger numbers. And so that's a distinguishing point. I just want you to understand that. So, and I don't know the actual origins of that, but that much I do know, so I'm sharing that with you. Okay, then we are learning the what they call the factor labeling method. The book calls it the factor label method, and I call it dimensional analysis. Let's be honest, if you sit down and say, Mom, I'm doing my dimensional analysis, it sounds a whole lot neater than if you say, I'm doing my factor label method. And it really is dimensional analysis, because the units, which are the dimensions, actually help us analyze what we're looking at. And so with dimensional analysis, we actually can convert back and forth between these different things. Now, I want to give you a heads up. Dimensional analysis is absolutely essential to chemistry. We have to be able to use this all the way through, not just converting between milliliters and liters or any of that. We're going to be using all sorts of unit multipliers or funky ones to get back and forth between different things in chemistry. And a lot of chemistry is memorizing the relationships to know how to build those funky ones. So it's very, very important. And if you're thinking, what is she talking about by a funky one? Let me show you. Turn over to page 12 and the first on your own. How I suggest you do this, and if you had physical science with me, then you already know this. When you're going to do any word problem, you should start by breathing. I don't know about you, but I get tense and I hold my breath. Don't do that. You'll pass out. So breathe. Pray, because you should always pray before you study. You should always pray before you read. You should always pray before you do the word problem. Don't wait till after the test to pray. You need to pray before you start on this stuff, okay? And ask God for His help. So you breathe, you pray, and ask Him for help and clarity of mind. And then you read the word problem twice. The first time you read the word problem, you do that because then you can go, I'm doing a word problem. And your brain just get used to the idea. And then the second time you read it, and you're looking for the given and the get to. And this works all the way through physics and other things, calculus. You look for the given and the get to. And then you write down the given and the get to. And if, like in physics or in chemistry, if there's an equation involved, then you would write down the equation also. But here we're just doing conversions. So let's look at the on your own, and I'll show you on page 12. On your own 1.1 says, a student measures the mass of a bag of sand to be 9,321 grams. what is the bag's mass in kilograms? So we have 9,321 grams, and we want to know what it is in kilograms. Now, I know some of you are looking at that and going, I don't have to do that here. I can do that in my head. But we need to know the method. We need to know how to do it. So we go times line, and this is the trick. Whatever unit is here always goes down here. And if you can go straight to whatever you're trying to get to from here to here, go ahead and put it up there. Now the trick is this. This has to be a 1, doesn't it? Because if we multiply any number by 1, it still retains its value. We can just make it look different. And that's what we're trying differently. And that's what we're trying to do. So whatever unit is here will always go down here so that it will cancel. Because this way it'll cancel and we'll be left with kilograms. Now, unlike the book, I don't like fractions within fractions. So I give whatever's the biggest one a 1. So I give kilograms a 1, and that means grams gets 1,000. And so in this case, we know that this is going to be 9.321 kilograms. And that's how we would do that one. Let's look at the next one. 1.2. If a glass container contains 0.465 liters of water, what is the volume in milliliters? So how I teach this, especially in physical science, is I tell them to write the given again, times line. And then whatever dimension is here goes on the bottom, because you want it to cancel. Whatever you're trying to get to goes on the top. Then I ask myself, who's the big boy, which is the liter? Remember the milliliters, the little bitty guy. I'm going to give this one 1,000. And then you multiply this out. Your liters will cancel. Make sure that lines up. Units are our friends. Units help us to know where the numbers go. So if they don't cancel, you know something's wrong. And then this is going to end up being 465 milliliters. Okay, let's look at on your own 1.3. On a professional basketball court, the distance from the three-point line to the basket is 724 centimeters. Yep, I'm seeing it right. 724 centimeters. And they want to know what is the distance in meters. So we're going to go times line. You look at what dimension's here. You put it down here so that it'll cancel. We can go right to meters. We know that a meter's this long, and the centimeters are the little guys, and there's 100 of them. And so that's going to give us 7.240 meters. So those are your easy conversions. Now next on table 1.3, he gives us the conversions between English and metric. And we can once again make really cool funky ones with that. So let's look at that. The on your own on page 13. How many kilograms? How many kilograms in 8.465 slugs? How many? Yeah, I'm right at that age where I don't want to wear my glasses, but I really can't see if the periods or commas or not if I don't. So please forgive me for that. And so slugs, we go times line. Don't even have to think. Just whatever your given is, you put times line next to it. Whatever dimensions here goes down here. Whatever you're trying to get to goes up here. Okay, but now we don't have a memorize something. And thank you, Jesus. You don't have to memorize this. It'll be given to you on your test. You look at table 1.3, but they'll give you the conversions on the test. And you see how many slugs there are in a kilogram. Now, I want you, this is what I've seen. I used to teach chemistry at a Christian school. I used to teach at a Christian school as well as to the homeschoolers. And I used to grade these tests. And I'm going to try to help you with the mistakes that I saw people make. What number, look at your table 1.3, what number is to the left of slugs on the table? That's right, 1.00. So you put that to the left of slugs here. What number's to the left of kilograms on your table? That's right, 14.59. So you're going to put it to the left of 14.59 here. I see students do all this and then they put the numbers in the wrong places. I don't want you to do that. So make sure that you put the number with the unit or the dimension that it's with on the table. Okay? Here, notice your slugs will go. And you'll multiply these two numbers together, and it will give you the answer in here. Just for those of you that just have to have the answer, 465 times 14.59 equals, and that gives us 3.5. Okay, and we're not working on significant figures right here. That's later in the chapter, so I'm just going to put that. Okay? All right, and then the next part, 1.5. 1.5 says, if the object occupies a volume of 6.1236 liters, how many gallons does it occupy? So once again, times line, whatever unit's here, has to go here. We're trying to get to this, and I can make a 1 out of this because of table 1.3. So I'm going to look at that volume, and this is going to get a 1. And this is going to get a 3.78. And so then we're just going to see this cancels. We're going to take this, divide by this, and we're going to get our answer. Now we can get into more complex unit conversion problems. And that is where we have to remember, oh, we're not multiplying them yet. What we're doing is we're going from like kilograms to milligrams or kiloliters to milliliters, where we don't know a funky one directly. And so these are fairly simple, though. Look on page 14, the on your own. It says a balloon is blown up so that its volume is 1,500 milliliters. And it says, what is its volume in kiloliters? So you would start the same way, write your given and your get to, times line. Write whatever your given dimension is down here, but I can't put kiloliters right up here because I don't know how many milliliters there are in a kiloliter. I don't have that memorized. But what I do know is liters is in both of them. So I'm going to go to liters, go to the common unit that's in both of them. And then I'm going to times line again, and whatever's here always goes here. And now I can get right to kiloliters, can't I? So I look at this, who's the big boy? This is the big guy, so this one gets 1,000. The kiloliters is like a hot tub, so there's 1,000 liters in it. If you always give the one to the big boy, you're going to have a lot of them have a 10 to the third in the other one, unless centi's involved. And then make sure this is lined up correctly, that everything goes away like it's supposed to, and then you have your answer, which is 1,500 times 10 to the negative 6 kiloliters, and then you would make it prettier than that. But I'm just trying to show you how to do these right now. Let's see. The 1.7 says if the length of a race car track is 2 kilometers, what is it in centimeters? So 2 kilometers, what is it in centimeters? So we're going to go times line, whatever you're given has to go here. Our common unit is meters, so I'm going to put meters up here. Then I go like this, meters to centimeters, because that's where I'm trying to go. Kilometers are the biggest ones. Here the meter is the biggest, and this is just 100 here, isn't it? This will cancel, this will cancel. So I end up with 2.0 times 10 to the 5th centimeters. You just go to the common factor. Let's look at 1.8. On 1.8, we have 0.01 megagrams, and we want to know how many milligrams are in there. So we go times line, megagrams down here, grams up here, grams down here, milligrams up there. So we have 1 megagram is, and if you can look back here to table 1.2, and it says mega is a million. Those of you that work with computers, you know that because of megabytes and all that stuff. So there's 1,000,000 grams here, and then 1 gram, there's 1,000 milligrams. And so this is going to be, okay, these cancel, times 10 to the 9th megagrams. And to make that right, I'd go like this, and I'd go times 10 to the 7th megagrams. Okay, but that's the idea, so that you know how to use that. Now, let's go on to something much harder, but it's real important, and I would like to make it as understandable as I possibly can for you. Before we do that, I was going on to significant figures, but before we do that, your book goes into derived units, and it points out that if you were to multiply x times x, you'd have x squared. If you were to add x plus x, you would have 2x. Units work the same way. If you were to multiply centimeters times centimeters, it gives you centimeters squared. If you add centimeters plus centimeters, you would have 2 centimeters. Works the exact same way as units. And so they don't just disappear. You have to treat them just like you would a variable in an algebra problem. Okay, so with that in mind, let's do an example problem. Oh, and on page 17, it gives us a very important piece of information. I showed you my little 1 centimeter block. See, it's one of those little centimeter blocks that you use in math. And this little centimeter block is a cubic centimeter. It's a centimeter on all 3 sides. If I filled this, I told you it would hold 1 milliliter because I'd have to do 1,000 times to fill my liter. This is also known as a cubic centimeter. CC stands for cubic centimeter. And so when a nurse measures a cubic centimeter, it's actually a milliliter or a cubic centimeter. So I just want you to know that because that's a bridge. That's a funky one that we'll be able to use a lot. And so let's look at the On Your Own problems on page 19. It says, should you be impressed if someone says she can hold her breath for 0.00555 hours? And so I'm going to go ahead and convert that into seconds. And I think everybody here knows the hint. So anyway, times line, I'm going to look at hours, and I'm trying to get to seconds, and I actually do know how many seconds are in an hour because I've done these so many times, but I'm figuring normal people don't. So let's go from hours to minutes. Everybody knows that in 1 hour there's 60 minutes, at least I hope everybody does. And then we want minutes down here, and we're going to go to seconds, and we know that in 1 minute there's 60 seconds. And so then we can go ahead and we take our number, 0.00555 times 60 times 60, and she can hold her breath for basically 20 seconds. So are we impressed? No, we're not. Make sure, everything cancels like it's supposed to, and it was 19.98 seconds. Not a big deal that you can hold your breath for 20 seconds. So that was the point they were trying to make, was go ahead and convert it so that you see what it really is. 110 says how many centimeters cubed are in 0.0091 kiloliters. And so we want to know how many centimeters cubed. All right, times line. We know we start there always. We have to put this down here. We want to get to centimeters and cubed. And we know that centimeters cubed equals milliliters. And so milliliters has a common factor here, doesn't it, with liters? So we're going to go like that, liters, and then we can go to milliliters. And once we get to milliliters, then we can put that down here and we can go to centimeters cubed, can't we? Because that's a 1-to-1. You're supposed to have that memorized. And so we have 1 kilometer, because that's the big one, and there's 1,000 of these in there. In 1 liter, we have 1,000 of these. And so here, let's make sure everything cancels like it's supposed to. And so that will leave you with 0.0091 times 10 to the 6th centimeters cubed. And then to make that pretty, putting it in scientific notation, we would go like that. It goes over 3, so it's 3 centimeters cubed. And if you don't know what I did, it's okay. We're about to cover that. Okay? So that's how you would do those. All right. Let's see. The last one there, 111, says the area of a room is 32 meters squared. And it says, what is the area of the room in millimeters squared? These are fun. You times line once again. And you're going to put meters down here. I don't put meters squared yet because I don't know how to make a funky 1 out of meters squared. I don't just have it memorized. But I do if I just use meters. So I'm going to go meters here, and I'm going to go millimeters here. Now I know in 1 millimeter there's 1,000, in 1 meter there's 1,000 millimeters, aren't there? Okay, now I have a funky 1, but I need this to be squared. So what I'm going to do is square the whole thing. As long as I do the same thing top and bottom, it still remains a 1, doesn't it? And so this down here is going to be 1 meter squared, and this up here is going to be 10 to the 6 millimeters squared. Okay, you see why I couldn't just do that. I didn't have that memorized. So I'm going to use this new funky 1. And so that's going to give me 32, these will cancel, times 10 to the 6 millimeters squared. And then if I were to put that in scientific notation, I would do it this way. Okay? All right, and so you need to remember, make this in the base unit where it's a linear, so no exponents, make it a 1, and then do the same thing to the top and bottom to get it to what it needs to be so that it matches that given unit. And then you'll have your new unit multiplier or funky 1 that you need to do that. Okay, now we get to making measurements on page 19, and they tell you here that when you make a measurement that you go ahead and start up on the ruler a little ways so that you get a more precise measurement. I don't do that personally because every time I do, I forget to subtract off the 1. So I'm telling you right now that if you don't want to do that, you don't have to. Just get a really good ruler that starts at 0. And the ones I buy, most of them actually have a mark that's a little ways in that starts at 0. I find that easier because I'm just that type of person that I forget. So I forget to subtract off the 1, okay? But that's up to you. But you're going to have to be able to do that on a test. Now, the next thing it mentioned here was making a measurement with a graduated cylinder. This is a graduated cylinder. And you notice the reason it is called a graduated cylinder is it is a cylinder. And it's graduated because it's marked off here in a graduated fashion so that you can measure volume in them. And we'll be working with graduated cylinders a lot this year. When you measure in a graduated cylinder, let's say this is 5 mils, 1, 2, 3, 4, 10 mils, okay, and on up. Okay. When you pour the liquid in, because of surface tension, the liquid will actually kind of make like a half of a bubble. It's called the meniscus. And we measure to the bottom of the meniscus. You don't measure to the top. And when you measure, that's as far as we're supposed to go now. But you've already read this. We're going to use our precision and accuracy correctly. So look on page 21. There's 2 words there, accuracy and precision. And if you're allowed to write in your book, even with a pencil, next to accuracy, I would say write the word person. And next to precision, write the word instrument. Because accuracy depends on the person and how well they're doing at measuring something. Precision depends on the instrument. It's telling you how far that instrument is calibrated to measure. Like in this instance, I have marked off this graduated cylinder to the 1s place. It's marked off 1 mil, 2 mils, 3 mils, 4 mils, 5 mils, 6 mils, 7 mil, 8 mil, 9 mil, 10 mils. So this graduated cylinder is actually precise to the 1s place. The 1s place, okay? When we looked at our ruler was marked off in centimeters. So these were our centimeters, 1 centimeter, 2 centimeters, 3. But I told you it had 10 lines in between. It was actually marked off to the milliliters, wasn't it? And so that would be the precision of this instrument, our ruler, would be to the millimeters place. So what does that mean? If it was 1 centimeter, let's say was a little over 1 centimeter, we measured something that was this long, then that would be 1.3 centimeters because it's actually marked out to that. Now that's the precision of our instrument. Our actual precision of our instrument in this case is to the millimeter place. So far so good. So your car odometer is marked off to the 10th of a mile. So its precision is to the 10th of a mile. Whereas our rulers are much more precise than that, aren't they? And our accuracy is how well we measure those things. And if you look over on page 23, they introduce the idea of significant figures. Now listen, first I want to tell you what they really are, because in college I thought people were just trying to torture us, okay? So listen closely. There's really a reason for significant figures. I was so glad to find that out. Significant figures, when we accurately report something that we're measuring, we are going to estimate 1 digit past the precision of our instrument. Did everybody hear me? When you're doing your measurement, you are going to estimate 1 digit past the precision of your instrument. That will give you the right number of significant figures. Okay, so what we have here is this is 5 mils, but it's already precise to the ones place. So I would accurately write that 5.0 mils. That tells me this digit is estimated. Every scientist on the planet knows that because he knows the last digit is estimated, therefore the precision of the instrument was right before that. It actually gives information, which is great. And so with this is not right as far as its accuracy on significant figures because this instrument is actually precise to the millimeters place, which means I have to have at least one more digit that is estimated for this to be correct number of significant figures for this particular, the precision of this particular instrument. Okay? So significant figures, so in other words, if I were to have a beaker, let's keep our little guy here. Okay? And let's say I had a beaker, and my beaker was measured off. It's a little beaker, so it's measured off to the 50 mil mark. So considering it's measured to the 50 milliliter mark, we're going to say that it's only precise to the hundreds place. Let's go ahead and say that, okay? So it's precise to the hundreds place. And so when let's say we had liquid in here and it looks like about 75 mils, you would write 75 mils, okay, but significant figure-wise, well, you know what, let's say it's to the tens place because it does have the 50. So significant figures-wise, this would be okay because the 7 would be the actual precision of the instrument. The 5 would be the estimated digit. And so that would tell us if this was to the tens place, because I'm just coming up with this off my head, that would be the proper number of significant figures for our answer. Now, you also are supposed to be learning rules about significant figures, and let me just show you this real quickly while I have this up here. Back to our let's see, 50 mils, and this was 100 mils, and so we had 75 mils of, approximately 75 mils of fluid in here. If I were to take this 5 mils and pour it into here, we said we had 75 mils, and here we have 5.0 mils, and we add this together. That would give me 80 mils. But look at this. This is much more precise than this instrument, isn't it? This is marked off all the way to the ones place. This is marked off to the tens place. So we can't give an answer that is this precise. It's just putting way too much precision in this for not enough in the actual instruments. So when you add or subtract significant figures, you have to answer in the least precise, in the same number of precision, not significant figures. You're not answering the same number of significant figures. You're answering in the same precision as the least precise. And so here, the precision's to the ones place. Here it's to the tenths place. So our answer can only go to the ones place. So you're going to get rid of this. And that's what the rule means on page 28, where it says adding and subtracting with significant figures. When adding and subtracting measurements, round your answer so that it has the same precision as the least precise measurement in your calculation. And that's what it's talking about there. So that's very important. And we'll come back to that. We'll be using this all year long. The other rule that's right below that says when you multiply or divide significant figures, which is much easier, you just come up with your answer, and then whichever thing, factor-wise, that you started with has the least number of significant figures, that's how many significant figures your answer has to be in. And I'm going to show you that in just a sec. First, let's figure out how to count significant figures, which would be helpful, wouldn't it? But now you know significant figures actually have a real value. The value is the significant figure tells you that they estimated one digit past what the actual precision of the instrument was. So there's a concrete reason to use them. If we're counting our significant figures, in your book on page 23, it gave you some rules. And let me give these to you in my rules.